So our last speaker today is a real trooper. He was recruited yesterday to sub for 2 other people. So when he makes mistakes, don't be hard on him up here. Of course, we probably won't know if there are any. But, Dr. Sattar Dorafshan joined the Federal Highway Administration Turner Fairbanks Research Center as a NRC postdoctoral research associate. His main area of expertise and interest is introducing automation to structural condition assessments and inspections using robotics and artificial intelligence. And before joining the FHWA, he was at Utah State University, where he obtained a PhD in civil engineering. Getting a lot of brain power during this session. So,
thank you.
I pass it to you.
Thank you. Just one question: how do I change the slides?
Uh-oh.
Something right there.
This one?
Yes.
Which bottom? Just the middle one? Thank you for the introduction. Good evening, almost evening, everyone. There's been a lot of talks about how do we use visualization for construction, management, new buildings, new infrastructure. But I don't think that's the problem with the highest gravity in our DOT and in our society. We have infrastructure, we have aging infrastructure that we need digital twins of them, we need BIM of them, or BIM models. And so because of that, we started a research project, kind of like a feasibility project, to see whether we can leverage different non-destructive evaluation data that we have for data fusion. And I'm going to talk about NDE data first. I'm going to talk about different data fusion approaches, the challenges, and some experimental results here, again, for existing infrastructure. So why do we use non-destructive evaluation methods? Basically, it's not possible to do a comprehensive structural evaluation without knowing the subsurface situation and the material properties of your existing infrastructure. So they're based on the type of defects, the components, and the material that we have. We use different NDE methods. One great resource that everyone can use is FHWA NDE web manual. You can find technologies that fit your inspection purpose. For instance, if you're looking for fatigue cracks or subsurface delamination in concrete, you can find a simple explanation and how to implement that. And why do we need the NDE? Again, for a better and more comprehensive evaluation inspection. And we also get better information rather than just a visual inspection. So the challenges with NDE, and this is from the feedback we got from DOT research engineers, that the bridge owners, they don't usually trust NDE because they're not sure if they're giving them the ground truth. And one of the reasons behind that is because visualization techniques are rather too extremely complex for them to understand, or too simplistic that they don't really provide any information. Another issue that they've been struggling with is having different types of NDE data and no way to combine them and kind of know which one is the right or correct or more reliable method. At FHWA, there was a workshop in 2016, and the outcome of that workshop indicated that we need data fusion in order to address these challenges. So the visualizations that we do with NDE techniques, it could be from an A scan, which is just a time series. It could be a B scan or a C scan that you can see here. That's a C scan, so you have the depth of the deck, you have the level of rebars, and that's from ground penetrating radar or GPR method. Or you have B scans that they're just like it's like a plane or a plan of the defects or the subsurface properties of the bridge. Or you have heat maps here, Again, this one I think is from impact echo method. So basically, it shows regions with delamination with red color, the sound regions with blue, and the in-between ones with green. Another interesting way to use the data that we have. Recently, DOTs and even Federal Highway Administration through LTBP program, we take visual images of our structures too. And one great use of it is to use those visual images to create a 3D model of the surface of the structure. So basically, we want to capture every structural defect on the surface through that 3D model using SFM, or structural from motion, and then multi-view stereo-based 3D dense 3D reconstructions. And then on the other hand, we have NDE techniques. In this case, they've used ultrasonic tomography and P-wave methods to kind of get a subsurface defect map of this concrete column. And they kind of combined it together into this interactive digital twin, if you will, of the reinforced concrete column. So the most immediate, when we talk to DOT people, the first thing they say, they compare NDE methods to medical imaging, and they're right on that. They're saying, for instance, a technician in a hospital takes the X-ray, takes the sonogram or MRI, and the doctor, without any prior knowledge about that imaging technique, could make a diagnosis. How come we don't have this capability for NDE? And well, one of the reasons is bridges are a little bigger than a human head, but anyways, we're working on that. But this is one of the things that everyone is, every DOT engineer, when we propose to them using NDE method, they say that. And we also found out that based on the personal preference and expertise, they prefer different NDE methods, even for the same defects. And the variation in material and construction detail also impacted the NDE selection. So, and again, they use multiple NDE techniques, and they don't know which one is the correct one and how to combine them. So the research objectives are, we want to kind of develop methods for visualization of the NDE data first. One of them is augmented reality, virtual reality, which is an ongoing research project. The second one is to come up with the ways to fuse the NDE data to make more reliable decisions. And we also want to integrate visual analytics into data fusion approaches. And finally, we want to work with the DOT engineers to understand the challenges and provide them with the best practice. So when we talk about data fusion, you can generally classify it in three different classes. You have data level, where you're using similar sensors or sources to get similar targets, or to create or to combine those two sensors to make a better decision to find a similar or the same defect on a structure. That's very common in structural health monitoring. Then you have the feature level, where you blend different sources of NDE or data, and through that you take some features of each NDE method, and you come up with different ways to combine them to improve the assessment and quantification. And then you have decision level, where you make decisions based on each NDE method, and then you enhance the decision making using all the available NDE methods that you have. Some prior work in visualization, I showed this image here before. Basically, what's done here, you have some sort of NDE method. You inspect your bridge or a specimen with it, and usually it's in the form of a signal or just a number, and you kind of map this number on a spatial location of the bridge. if your NDE method is advanced enough, it would allow you to pick different depth of that specimen and kind of map that out. And if you have different depths, basically you can now create a 3D model just by putting all these different depths together and connect them, which leads to this 3D model here with the defects, rebars, and everything showing. And one of the challenges with that is we can't yet do that for infrastructure inspection in real time. You still need to take the data, gather the data, take it back to the office, and run some analysis to kind of create that 3D model. It's not done yet, but it's mostly done with the defense applications and first responders, as far as I know. On data fusion, mostly it's been done on biomedical imaging and research because they have NDE-like data. It's been done for structural health monitoring, but as I said, it's more on the data level fusion. So basically, imagine they're taking two different images from two different cameras from a crack, and they're monitoring that crack. And they use the two images to achieve a higher accuracy in crack detection, which is not really something that we look for when it comes to subsurface defects. And they basically deal with a different problem. With NDE data fusion, this is one of the earliest attempts where they used, I believe they used GPR to detect, or some sort of radar-based method to detect the red ones, the red regions, which are the shallow regions of the concrete with coloride content, which indicates corrosion. And they used half-cell potentials, if I'm not mistaken, for the dark ones, which are a deeper coloride content. And they're kind of put those results of each NDE method together for a better decision making. So if you get that picture, and basically the white regions are supposed to be sound concrete. So this is a better visualization instead of just having different NDE heat maps separately. This is actually giving us a better understanding of what's happening under the surface of the concrete. So the challenges with NDE measurement uncertainty is that different operators, they come up with different results because we still need the experts in NDE to look at the data and analyze it as of now. And it could be different from scan to scan. Many of the conventional data fusion techniques that there already exist, we cannot use for NDE data. As I mentioned, SHM or structural health monitoring, different problem. So we move towards using machine learning and deep learning approaches to address these challenges, but they need a lot of data to work well. So basically, with the machine learning algorithms, we take the measurements of each input. And when we have a lot of that data, we can kind of train a computer algorithm for future predictions. So when it's introduced with the new data, it wouldn't need a human expert's opinion on the data, and it can make decisions on its own. The drawback on using that is that we're introducing another uncertainty to our problem. So we had uncertainties associated with each NDE method, and now we're combining them together using artificial intelligence, and that's another uncertainty added to the problem. But on the other hand, it would enhance the visualization and can increase the reliability of the defects or heat maps. So we had 8 reinforced concrete specimens with internal defects. We had shallow delamination, deep delamination, honeycombing, and voids. And we also had corroded rebars, which are shown here in red. And we wanted to see if we can use the data that we took from these specimens. We took several NDE methods. If we can combine them together to find two types of defects, basically corrosion and delamination, using all those three methods, basically basic logistic regression, support vector machine, and neural networks. So the graph you see on the right is called receiver operating characteristic, or ROC curves. It's a very well-known metric when you have any sort of artificial intelligence approach. Basically, the greater the area under the curve is, it means your machine learning or algorithm is more robust. So first, as you can see here, we're trying to find corrosion, and we're using three NDE methods. We're using GPR, ground penetrating radar, electrical resistivity, and half-cell potentials. If you use each NDE method, you can see that their performance is not that great, except for the half-cell potential, which reaches to the area of 0.992, which is rare. It doesn't happen all the time in practice. But we got really good results from half-cell potentials in the lab. Then we combine the result, or the analysis result, using logistic regression from electrical resistivity and half-cell potential, and then we just went with combinations of two, and then finally we went for a combination of all three NDE methods. We noticed that this logistic regression is not the best way to combine the data together, because you cannot see the improvements very tangible from, for instance, if you have half-cell potential with 0.992 area under the curve, you still have the same number when you use data fusion. So we went for the alternative methods. Support vector machine is a very famous machine learning approach for different data, basically any type of time series that you have, or images even. You can use support vector machine to extract features and combine them together. And with that, we saw more promising results. So you can see when we use single NDE, the area under the curve is kind of small, for the exception of half-cell potentials again. But with the use of support vector machines, or SVMs, we can leverage the data fusion, and you can see the gradual improvement for this metric over when we use two NDE methods and when we use all three together. And we actually got a better overall area compared to the last or previous data fusion technique. On the right, you see a defect map. It's basically it gives you the algorithm confidence, SVM confidence on different locations from fusing all the data together. So the red ones shows that the algorithm is like 100% almost sure that there's like corrosion here, and the blue ones are like sound concrete or rebar. The second type of defect we were interested in is delamination. It was a little trickier to work with delamination, because one of the most common techniques to detect delamination is called impact echo method. And with impact echo, you're dealing with a vector rather than a single point. So first, you need to extract features from your signal. And one of the ways to do that is called peak frequency analysis. So you basically take the time series, you transform it to frequency domain, you find the peak value, and based on that peak value and the thickness of your concrete, you can make a decision whether there was a subsurface defect and the location of the impact echo or not. Interestingly, we saw that if you use only impact echo, even in the lab setting, the results are like flipping a coin. So half the time you get what you want, the other half you don't, kind of like praying. And with the kind of combining that with the electrical resistivity and GPR, we kind of see a gradual raise here up to 70%, which is not that great, but still you can see data fusion is working. We figured maybe there are better ways to get that feature from the time series. because as I said, GPR and electrical resistivity, there are single points, whereas impact echo is a time series. This time we tried wavelet analysis, and we got the feature from our signal using the wavelet analysis for the impact echo. And as you can see, we're getting now higher and better results here, up to 0.83. We also asked whether, in terms of visualization, what's more preferable. The common wisdom is DOT people don't like the complicated visualization, and they go with the simplest one. So we asked them whether you like to have this heat map here as a binary heat map. So you set a threshold value on the confidence level, and anything below that you say it's intact. Anything over that you say it's defect. So you can either present them in this way, or you can actually give them the confidence values. And most people, most of the responders, they preferred this one. Just have the probability or the confidence for them to make a decision. So I talked about peak frequency method and wavelet transformation. There's another way that you can extract features from your data, basically any type of data that you have, and it's called deep learning. I'm not going to get really technical here. This is one of the slides I put together for a class I taught last semester. So basically you have data, doesn't matter what type, it could be pictures, time series, whatever. You have an inspector, a human expert that annotates that data into, in my case, defect and intact regions. And then you come up with the algorithm. It's called deep learning model using convolutional neural networks. So to do the training on this annotated data set. So basically, it goes back and forth and determines maybe millions of parameters within this algorithm. Once the training is complete and you're sure of the performance of your model through validation, now you can introduce new data set to it, and this trained model would make the same decision as a human inspector, and sometimes even better than a human inspector. So that's the whole idea behind it. So you saw the challenge with the impact echo. So I went ahead and we had 8 bridge decks. So I said, what happens if I know the location of the defects? What happens if I come up with a model based on the location of the defects for subsurface defect detection using deep learning? And I trained on 8 bridge decks, and I tested on the on 7 bridge decks, and I tested on the 8th one. So you can see here on the top is the conventional analysis, peak frequency analysis, and as you can see, there are like a lot of false positives here. So these white rectangulars, they're showing the location of the defects. Like as I mentioned, we had shallow delamination, deep delamination, voids, and honeycombing. The one in the bottom, and again, like this peak frequency value doesn't make sense if you don't know the physics behind the impact echo. Like you don't know what it means. Versus this one, which is a deep learning approach, it gives you, instead of peak frequency value in kilohertz, it gives you probability of defect presence in different regions of the deck. So this is kind of like that medical imaging. Now, the inspector doesn't need to know anything about impact echo. He can just look at this defect map or heat map and says, oh, okay, so there's like 80%, 90%, 100% probability that there's a defect here. These regions are sound. So we found out that deep learning is not even only feasible, but is really helpful for this. But again, just like anything else we do, there are limitations. Most important one, we did this in a lab setting, and we didn't account for realistic field data acquisition and condition. Like we didn't consider the noise, the environmental considerations, and we also knew where the defects were. So the operator of the NDE would make sure that they capture those defects when they were conducting NDE testing. Also, we realized that the material variability is a major challenge. in our way, and we didn't account for that in our study. We only used one type of concrete, one type of rebar, and we need to build a better data set for the future implementation. And we know that the results might be biased by the nature of the laboratory methods. As you saw, the half-cell potential was giving us surprisingly good detection rate, which is not always the case when you inspect the bridge. So we have a couple of ongoing works. We're expanding the study of the field results. We have an existing NDE data from Rabbit, which is a part of our long-term bridge performance program. And we are also conducting and gathering new NDE scans at Turner Fairbank Highway Research Center. We're also looking into augmented reality for 2D and 3D visualization and see if we can actually improve the structural assessment through that. I think that's my last slide. Thank you for your attention, and if you have any questions. Yeah.
Could you use, like, if you did all this data stuff, could you use augmented reality live, like as you're walking across the bridge?
In theory, you could. I haven't seen anyone actually come up with a way in real time, but we have the software and hardware requirement for it. That's one of the things that we're looking into. I think it's still in the laboratory validation phase, not in the actual inspection yet.
How long does it take to look at it?
What thing? The augmented reality?
No, I mean, it seems like all of the data.
Oh, okay. So it depends on your device. There are different devices. So, for instance, Rabbit has it's a robot. It goes on the bridge. It has NDE trays on the front and the back, and it has 2 cameras, visual camera, and it takes data every 2 feet along the bridge. You can also use manual devices to collect the data. It depends on your resource, basically. Yes.
How feasible is this to use for mining environments from underground or natural settings? When you hear in other countries some experts.
So I know GPR has been used to detect underground objects, which is one of the applications in mining, I think. I don't think impact echo or half-cell potential. So because half-cell potential and electrical resistivity are usually used to detect chloride-induced corrosion. So that's something that you only pretty much see in reinforced concrete structures, especially in bridge decks, not in a mining environment. But GPR has been used to do that. And there are actually a couple of really interesting deep learning approaches on that where they found something. They were looking for land mines, actually, and they were able to detect them through GPR, through artificial intelligence. Mm-hmm.
Any other questions?
Do you envision the deep learning effort that takes place to do the lab data analysis can actually transfer into live field data, or will that?
That's what I'm working on right now. So yeah, I'm gonna say I hope it does. Otherwise, I wasted almost 7 months of my life. But it has the potential for sure, and we've seen indications and the feasibility studies that we've done. I don't see why not. But again, there are always issues that comes up when you introduce a new technology to something that's been done traditionally. There are things that we don't necessarily account for during the feasibility study, and we face them in real life. So we'll see. I'm optimistic.
Well, very good. Thank you.
Thank you. Thank you.